In this video, we'll be looking at heat transfer, which consists of both conduction and then convection. So now we know that for convection, it involves the heat transfer between a solid surface and then a fluid, either being a gas or a liquid. And then for the conduction, it involves only two solids. Right? So now the question says that one side of a plane wall is maintained at 100 degrees Celsius, while the other side is exposed to a convection environment having temperature of 10 degrees Celsius. Now you can sketch our wall, and then you are seeing that this side is 100 degrees Celsius and then this side is 10 degrees Celsius. But then this side is exposed to a convection environment. This side, the question didn't tell us that it's exposed to a convection environment. Now you have a convection environment here. The wall has K, so our thermal conductivity of the wall is 1.6 watt per meter Kelvin and 40 centimeter thick. So our thickness is 40 centimeters. Calculate the heat transfer rate through the wall. So now we know that when one side of the wall is 100 degrees Celsius and then the other side is 10 degrees Celsius, then definitely heat will be transferred from the 10 degrees Celsius from this side from the 100 degrees Celsius at this side to the 10 degrees Celsius at the other side, and that becomes heat by conduction. Now, we know that there is ambient fluid here, or let's say atmosphere, a convection environment. Now, with a convection environment, we can assume that the temperature is at ambient condition, so 25 degrees Celsius. Now, at this 25 degrees Celsius, we can also see that this 25 degrees Celsius is actually going to lose heat to this surface at 10 degrees Celsius because this has higher temperature than this. Now, the total heat involves heat of conduction plus heat of convection. We just have to find them separately. Now, for heat of conduction, you know that you have to use the Fourier's law, which is negative K A T1 minus T2 all over the thickness. So from the previous video, I said that the moment you make a negative here, then it means you are going to use the smaller temperature or the colder temperature minus the hotter one. Now, because you don't have any idea about the area of the wall, then we can just divide through by area and get K over A equals negative K T1 minus T2 all over change in X. Now, our change in X is our thickness, which is 40 centimeters, and that gives us 0.4 meters. Our T1 becomes our colder temperature, 10 degrees Celsius, and our T2 becomes our hotter temperature, 100 degrees Celsius. So Q over A becomes, our K is 1.6 watts per meter Kelvin. So this is it. We can write it there, negative 1.6. So let's bring the unit so that it becomes easier for us to know our final unit. Our T1 is 10 minus T2 100. So like I said, because we are finding a change in temperature, change in degrees Celsius is the same as change in Kelvin. So we can represent that with Kelvin. And then our thickness is 0.4 meters. So Kelvin cancels Kelvin. And then we are left with Q over A being equal to negative 1.6 watts per meter times 100, 10 minus 100 all over 0.4 meters. And this gives us 360 watts per meter squared. Now, our heat of conduction is 360 watts per meter squared. So let me confirm the answer in C. 10 minus 100 over 0.4. Yes. So now we go back to the heat of convection. Now we know that for heat of convection, we can resort to the Newton's law of Coulomb, which is HA multiplying T infinite minus Ts. We don't know the area of the wall surface. We are going to divide through by the area. And then we'll be getting Q over A being equal to H multiplying T infinite minus Ts. Now, T infinite came here first because it's the one actually going to lose the heat. And this is actually going to absorb the heat because this has 25 degrees Celsius and this has 10 degrees Celsius. Now our Q over A equals our H is 10 watts per meter squared Kelvin. So 10 watts per meter squared Kelvin. And then our T infinite was 25 minus 10 Kelvin. So Kelvin cancels Kelvin. And then we are left with 10 multiplying 25 minus 10. So 10 multiplying 25 minus 10, we get 150. So 150 watts per meter squared. Now you realize that they both have the same unit. Now our total heat transfer will be equal to 360 plus 150, and that gives us 510 watts per meter squared. So this becomes our heat transfer rate through the wall.